Topic for today, partial fraction decomposition. So what we're going to be doing is we're going to be getting expressions like the one on the left here, and we're going to be breaking them down into the sum or difference of fractions. But before we do this more complicated ones, what I want to do is do a really simple one just so we get the concept of it. So let's say we wanted to add 1/2 plus 1/3. Well, pretty easy. We'd have to get common denominators, and the common denominator, of course, is 6, so this fraction would multiply 3 over 3. This fraction, 2 over 2, and then we would have 3/6 plus 2/6. Now, once the denominators are the same, of course, we add the numerators, so our answer would be 5/6. So again, what did we just do? We added 1/2 plus 1/3, and we got 5/6. Okay, so now what I'm going to do is I'm going to go backwards. Okay, so what if I gave you the 5/6 and I asked you what two fractions add up to 5/6? Now again, we're going to play dumb here because we know what the answer is, right? It's 1/2 plus 1/3. But let's pretend we didn't know. How do we do this? Well, the technique is fairly simple. The first thing we do is we factor the denominator. Okay, so I can do that. So the 6, that is the same thing as 2 times 3. Now, once you've factored, you get each factor and you write that as a fraction. In other words, I'm going to have two fractions here, one with a denominator of 2 and one with a denominator of 3. Now, I don't know what the numerator is, so I'm just going to call that a for constant a and then some other constant b. Again, we're playing dumb, right? Because we know the answers are 1/2 plus 1/3. But let's pretend we don't know. Okay, so what do we do next? Is we come to this fraction right here, and we're going to multiply the whole equation by the LCD, the lowest common denominator, in this case 6. So the 6, we're going to multiply it 3 times. Once here, and once here. All right, so let's see what we get. So on the left-hand side, we're going to be left with 5 because the 2 times the 3 is the same thing as the 6, and those cancel out. When I multiply the 6 times the a, well, I'm dividing by 2, so 6 divided by 2 is 3. And then similarly over here, 6 divided by 3 is 2, so we get 2b. So again, what we're after is we're trying to solve for a, and we're trying to solve for b. Now, look at the equation that we have. We have 3 times some number a plus 2 times some number b is equal to 5. So this one we can pretty much just say, well, if a is 1 and b is 1, we'd have 3 plus 2, which is 5. So bingo, we got it. So the a is 1, the b is 1, and we're supposed to act surprised because of course we knew the answer, right? So this a was 1 and the b was 1, which we knew. All right, so now let's apply the same technique to a much more complicated expression. Okay, here we go. So this one's much tougher. What we're trying to do is get this rational expression. Remember, rational expressions is just a fancy way of saying fractions. So we have this fraction with variables here, and we're trying to break it down into two fractions, 2 or more. Okay, so how do we do that? Well, the first thing we do is we factor. So go ahead and factor the denominator, okay? Always the denominator. Don't mess with the numerators. Leave the numerators the way they are. So we're going to factor denominator. Okay, so that shouldn't be too bad. So we're going to factor into two binomials. So let's see. So we know that x times x gives me the x squared. To get the 6, of course, we could try 1 and 6 or 3 and 2. Now, of course, the 3 and the 2 are going to be the ones that work, especially if we put a negative here and a positive here. Okay, so we're going to have the minus 3x and the positive 2x gives me the negative x. All right. So that shouldn't be too bad. If you're rusty on your factoring, just go ahead and review some factoring, okay? Because we're really going to need it in this section. Okay, so from here, what we're going to do is we're going to write our fractions. Now, the first fraction is going to have a denominator of x minus 3. The second one is going to have the denominator of x plus 2. Now, what are the numerators? We have no idea. So I'm just going to call them a and b. I mean, you can use whatever letters you want. You can try c and d, but we typically just start with a and b. Especially as we do some of the more complicated ones, we'll pretty much need to go through A, B, C, D, E, F, and so on. Okay, so what do we do next? So next, I'm just going to scroll down a little bit here, and I'm going to get rid of all the fractions. So the way I'm going to get rid of all the fractions is I'm going to multiply the whole equation by the LCD. Okay, remember, LCD stands for lowest common denominator, which in this case is going to be, well, x minus 3 and x plus 2. Now, how many times are we going to multiply this in? We're going to multiply it in once here, and once here. On the left-hand side, everything cancels except the x plus 7. For our first term here on the right, we've got an x minus 3, so this x minus 3 and that x minus 3 are going to cancel. So then what we're going to be left with is the a and an x plus 2. And then very similar with the last term here, the x plus 2's are going to cancel, so we're going to be left with our b and the x minus 3. So from here we have a couple of tools in our toolbox here. So the first technique we're going to try here is strategic substitution. Okay, now what does that mean? Keep in mind we're trying to solve for a and b. So what I'm going to do is I'm going to let an x be equal to negative 2. Now why in the world negative 2? Well, look, if I plug in negative 2 here, negative 2 plus 2 is going to give me 0. And 0 times a is going to make the a disappear. Okay? And that'll only leave us with the variable b, and we'll be able to solve for b. So let me show you. So we're going to plug in negative 2 every place you see an x. So on the left-hand side, we're going to have negative 2 plus 7, which is 5. Okay, so that wasn't too bad. For this term here with the a, the negative 2 plus the 2, of course, that's 0. So a times 0 is just going to be 0. So I'm not even going to write it anymore. And then when I plug it in over here, I'm going to have the b and then the negative 2 minus 3. So those two are negative 5. And with times the b is going to be minus 5b. So see, this strategic substitution is going to allow us to solve for b very easily. So simply we divide both sides by negative 5. So the b is equal to negative 1. Okay, bingo, we've got one of our terms now. Okay, so now I'm going to do the same thing again, but this time it's going to allow me to solve for the a. So to solve for the a, we have to get rid of the b. So this time we're going to let the x be equal to 3, because 3 minus 3, poof, 0, right? So let's plug in. So when I plug in a 3, 3 plus 7 is going to be 10. 3 plus 2 is 5, so this is 5a. And then when I plug in the 3 over here, I'm going to write it, but I don't need to, because it's 3 minus 3, which is 0. 0 times b is 0, okay? So the only thing we're left with is 10 equal to 5a. So of course, we solve for a, so a is equal to 2. So we're done. We're pretty much done because we've solved for our a and we've solved for our b. So now we can go back, and up here, instead of a and b, we write their equivalences. So the a was a 2, the b was a negative 1. And we are done. Okay, we have broken down our rational expression into two fractions. Now I'm going to just simplify them a little bit. So I'm going to write this as 2 over x minus 3. Now notice there's a plus here and a negative. So I'm just going to write that as a negative or a subtraction, and then I'll put a 1 over x plus 2. And we are done. So let's try a partial fraction decomposition that's a little bit trickier. But again, remember, we always start out the same way. We first make sure that the denominator is factored out. If it's not, then we go ahead and factor it out. So we do have a trinomial in the denominator, which we're going to try and factor into two binomials. Now we know that x times 2x is going to give us a 2x squared. To get a 1, of course, it's 1 times 1. Then we play around with the signs and figure out that a negative and a positive are going to work. So this is our setup for the partial fraction decomposition. We know we're going to break it up into the sum of two fractions. So the first fraction is going to have the x minus 1 in the denominator. The second fraction is going to have 2x plus 1. Now a little bit of vocabulary here. So the denominator, we factored it out into two linear factors. And of course, we don't know what the numerators are, so we just assign them a variable, or in this case, just a and b for simplicity. Now what we'll do next is we'll multiply the whole equation by the LCD. So what we'll do next is we'll multiply the whole equation, everything in the green brackets, by the LCD. And we're going to multiply that LCD 3 times, once times each fraction inside the brackets. Now, what's going to happen when we multiply the LCD? Well, the beauty is, poof, all three fractions are going to disappear. So when we multiply the LCD by the left-hand side of the equation, both the x minus 1 and the x plus 2 cancel. We're only left with the numerator, which is the x plus 5. Now, the first fraction on the right-hand side, only the x minus 1 cancels. So we're left with an a times the 2x plus 1. And similarly, with the b, the 2x plus 1 cancels. So we're left with b times the x minus 1. See, so the beauty is now we have an equation and we do not have any denominators. And now we can use that technique that I mentioned before, and it's called strategic substitution. In other words, we look at the variables. So here are the x's, and I'm going to look at the last term that we have here, the b times the x minus 1. Okay, so right here. If I let x equal to 1, then the x minus 1 is going to cancel because 1 minus 1 is 0. And 0 times b, it's going to cancel the b, and we'll be able to solve for the a. So let me show you. First thing, we plug in a 1 every place you see an x. Once we plug in the 1, let's see what happens. We're going to get a 6. We're going to get 3a plus the 0. Of course, we don't need to write the 0 anymore, but I just put it in there. And we are pretty much done, well, at least with the a, because now we know the a is equal to 2. Okay, so what I'm going to do is I'm going to go up here, and instead of the a, I'm going to plug in the 2, because now we know what it is. Awesome. All right, great. So from here, I'm just going to erase my work here. I'm going to also plug in the a right here. And now our goal is to solve for the b. B as in boy. So how do we solve for the b? Well, there's a couple of ways, but we can pretty much just plug in any number other than the one we've already plugged in for x, which is 1. So I'll tell you what, this time I'll plug in a 0. Okay, so we're going to let x equal to 0 and check out what's going to happen. Now we do a little bit of arithmetic. So 0 plus 5 is 5. This is a 2 minus b. So we solve for b, so the b is equal to -3. And we are done. So now we go back up right there to the numerator and we plug in our b. So nice. So let's clean up our work here, and we are pretty much done. We'll just a few more comments here. Let's zoom in a little bit here. So what I'm going to do is I'm going to combine both positive and negative right here. Just write it once as a negative, and now we are done. Okay, so let's review really quick. So the first thing we did was we factored the denominator, and we factored that into two linear factors. We got both linear factors and we wrote them as two separate fractions. Now, of course, we didn't know what the numerators were. That's where we used a and b. But then once we multiplied the whole equation by the LCD, all the fractions went poof, and we were able to use strategic substitution to solve for our a and our b. And we are done. We have successfully broken down the fraction into the difference of two fractions. Awesome. So let's try a partial fraction decomposition that's a little bit trickier. But again, remember, we always start out the same way. We first make sure that the denominator is factored out. If it's not, then we go ahead and factor it out. So we do have a trinomial in the denominator, which we're going to try and factor into two binomials. Now we know that x times 2x is going to give us a 2x squared. To get a 1, of course, it's 1 times 1. Then we play around with the signs and figure out that a negative and a positive are going to work. So this is our setup for the partial fraction decomposition. We know we're going to break it up into the sum of two fractions. So the first fraction is going to have the x minus 1 in the denominator. The second fraction is going to have 2x plus 1. Now a little bit of vocabulary here. So the denominator, we factored it out into two linear factors. And of course, we don't know what the numerators are, so we just assign them a variable, or in this case, just a and b for simplicity. Now what we'll do next is we'll multiply the whole equation by the LCD. So what we'll do next is we'll multiply the whole equation, everything in the green brackets, by the LCD. And we're going to multiply that LCD 3 times. ones times each fraction inside the brackets. Now, what's going to happen when we multiply the LCD? Well, the beauty is, poof, all three fractions are going to disappear. So when we multiply the LCD by the left-hand side of the equation, both the x minus 1 and the x plus 2 cancel. We're only left with the numerator, which is the x plus 5. Now, the first fraction on the right-hand side, only the x minus 1 cancels. So we're left with an a times the 2x plus 1. And similarly, with the b, the 2x plus 1 cancels. So we're left with b times the x minus 1. See, so the beauty is now we have an equation and we do not have any denominators. And now we can use that technique that I mentioned before, and it's called strategic substitution. In other words, we look at the variables. So here are the x's, and I'm going to look at the last term that we have here, the b times the x minus 1. Okay, so right here. If I let x equal to 1, then the x minus 1 is going to cancel because 1 minus 1 is 0. And 0 times b, it's going to cancel the b, and we'll be able to solve for the a. So let me show you. First thing, we plug in a 1 every place you see an x. Once we plug in the 1, let's see what happens. We're going to get a 6. We're going to get 3a plus the 0. Of course, we don't need to write the 0 anymore, but I just put it in there. And we are pretty much done, well, at least with the a, because now we know the a is equal to 2. Okay, so what I'm going to do is I'm going to go up here, and instead of the a, I'm going to plug in the 2, because now we know what it is. Awesome. All right, great. So from here, I'm just going to erase my work here. I'm going to also plug in the a right here. And now our goal is to solve for the b. B as in boy. So how do we solve for the b? Well, there's a couple of ways, but we can pretty much just plug in any number other than the one we've already plugged in for x, which is 1. So I'll tell you what, this time I'll plug in a 0. Okay, so we're going to let x equal to 0 and check out what's going to happen. Now we do a little bit of arithmetic. So 0 plus 5 is 5. This is a 2 minus b. So we solve for b. So the b is equal to -3. And we are done. So now we go back up right there to the numerator and we plug in our b. So nice. So let's clean up our work here. And we are pretty much done. We'll just a few more comments here. Let's zoom in a little bit here. So what I'm going to do is I'm going to combine both positive and negative right here. Just write it once as a negative. And now we are done. Okay. So let's review really quick. So the first thing we did was we factored the denominator, and we factored that into two linear factors. We got both linear factors and we wrote them as two separate fractions. Now, of course, we didn't know what the numerators were. That's where we used a and b. But then once we multiplied the whole equation by the LCD, all the fractions went poof, and we were able to use strategic substitution to solve for our a and our b. And we are done. We have successfully broken down the fraction into the difference of two fractions. Awesome. So how do we check to see if our answer is correct or not? Well, what we could do is we could simply work backwards. We work from our answer, which is two fractions that are being subtracted. Go ahead and subtract those two fractions, and it should give us where we started out with. So this is a very useful technique, especially on a test. So double check your work, because if you go backwards, you should get where we started. Then if you don't, then you can quickly go through your work and hopefully find your mistake. Awesome. So let's jump into it. So we're going to get the answer and we're going to work backward. So it's just subtracting of two fractions. So what we do is when we add or subtract fractions, we have to get the common denominator. And the common denominator is each of the linear factors that we have. Now the first fraction, we have to multiply that one by whatever it was missing. In that case, the 2x plus 1. Both numerator and denominator. The second fraction, we multiplied by x minus 1, both top and bottom. So let's just do the work. So this 2, we're going to multiply it. Same thing with the 3. We can also call that distribution. So we get 4x plus 2 minus 3x minus 3. Aha! There's a small mistake. Let's see if you can catch it. So here, we need parentheses here, or simply remove the parentheses and change the last sign to a positive. Okay, so what I'm doing is I'm distributing this negative right here. Okay, because the 3 times the x gives us the 3x, and the 3 times the negative 1 gives us a minus 3, but when you multiply times a negative, it makes that last sign a negative. Okay, so that's where we have to be careful, those small little mistakes. So let's rewrite this. We're going to combine like terms. So 4x minus 3x is simply x, and the 2 plus the 3, that gives us 5, and we're done. You see this right here and this are identical. So we've checked our work. We got exactly where we started from. Awesome. So this is a really good technique. It's pretty quick, and especially on a test where if you get it wrong, you're gonna lose a lot of points, right? So it's always a good idea to check your work, because if we had not gone where we started, then we know there's a mistake somewhere. Then you can go back and catch your mistake. So let's try one with a quadratic factor. So like always, we always start in the denominator. So we always start by factoring the denominator if it's not factored. In this case, it's not. So in the denominator, there's 2 terms, and they both have an x, so we factor it out. So of course, the first fraction, just like before, we're going to put the constant a, the unknown constant a, over x. And then we're going to add another fraction with the denominator, which includes the quadratic factor. So here is where it's a little bit different, okay? So notice that since we have a quadratic factor in the denominator, the numerator always has to be 1 degree less. Now, this is the first time I mentioned this because it's the first time we're actually going to need it. Let's go back to the first fraction. See, the power here is a 1. And in the numerator, we just have a constant. So that's 1 degree less. Degree means the power. So very similarly here on the second fraction, the denominator is quadratic, meaning a power of 2. So the numerator has to have a power of 1. That's why I wrote it as a linear expression. So that's a little bit different, but this is the first time we need it. Now what we're going to do from here is no different than what we've done in the previous examples. Okay, so we multiply by the lowest common denominator, which is x times x squared plus 4. Now, you multiply when it's in factored form. Okay, it just makes things easier. Now, what happens when we multiply the LCD? Well, a bunch of poofs. In other words, we're going to get rid of all the fractions. All 3 denominators are going to cancel out. But before we can do that, this LCD has to be multiplied in 3 times. 1s times each fraction. So here we go. On the left-hand side of the equation, the whole LCD cancels. On the right-hand side, in the first fraction, the x's cancel, but we're still left with an x squared plus 4. And on the second fraction on the right-hand side, the x squared plus 4 cancels, so we're left with an x that we have to multiply times the numerator of bx plus c. Now notice I put in some parentheses there. Be sure and print those parentheses, otherwise you're going to mess up the problem. We don't want to do that, okay? So see, now you know why I said poof, because all the fractions just poof, they disappeared, and this is going to happen every single time. Guaranteed, if you multiply it by the LCD. If it doesn't, that means you screwed up somewhere. So double check your work, okay? Now in this problem, it's going to be a little bit more challenging because we have 3 constants to solve for. We have to solve for the A, the B, and the C. That's why I color coded them orange, just so that we don't forget what we're trying to do here, okay? We're trying to figure out what that A, that B, and the C are. Because once we know those, then we'll know what our partial fraction decomposition is. Okay, so how are we going to do it? Well, let's go ahead and use that strategic substitution that I've been using. Now, what I would do is I would let x be equal to 0. The reason for that is because all of this is going to cancel, because if I plug in a 0, the 0 times the bx plus c is going to just poof, cancel out. And then we'll be able to solve for our a. Okay, so let's go ahead and do that. So I plugged in the 0 and a bunch of stuff is going to cancel out. Okay, so check it out. On the left-hand side, we're only left with 4. That's it. Because everything else, all this, poof, just cancels out to 0. Now on the right-hand side, we're going to have 4a plus all this is going to be big fat 0. Because anything times 0 is going to be 0. Okay, so this 0 right here just cancels everything out. Awesome. So of course we solve for our a, and our a is 1. So I'm going to go up here, and instead of the a, I'm just going to type in my 1. Boom, we got it. Okay, so now we just need to figure out what the b and the c are. So I'm going to do some cleanup here. Now I'm going to show you a new technique. Instead of strategic substitution, we're going to use equating coefficients. Now this is the first time I show you this as well, so let me show you what that is. So the left-hand side of the equation is in general form of a polynomial. General form meaning the powers are decreasing. See, we've got an x squared, we got an x, and then the constant. So we're going to do exactly the same thing on the right-hand side. So that's the first step we'll do when we're going to use this new technique that's called equating coefficients. So on the right-hand side, I just kind of simplified everything out. Now I'm going to combine like terms. So the first term and the third term are x squares. So what I'm going to do is I'm going to factor out the x squared, and I'm going to have 1 plus b quantity x squared. Next, I'm going to write the linear term, which is the x. Keep in mind, because we're trying to put it in general form. So put a little reminder here on the left-hand side. So we're trying to convert everything into general form, okay? So the left-hand side was already in general form, and we just finished doing that with the right-hand side. So notice that on both sides of the equation, we have 3 terms. 1, 2, 3, 1, 2, 3, okay? And that's exactly what we wanted, and they're both in general form. Now, we're reminded what an equation is. An equation obviously is that the left-hand side has to be exactly the same thing as what's on the right-hand side. So then that allows us to equate the 3 to the 1 plus b. In other words, those two have to be the same. So we form a little equation here. So we're going to say 3 has to be equal to 1 plus b. So that allows us to solve for b. So b is equal to 2. Awesome. So we got our b now. And then very similar with the c, this right here, we're going to equate to this, okay? So then the c has to be equal to 4. And we're done, because we had solved for the a. Now we just found the b and the c. I'll go up to the top line, I'll erase the b and the c, and I'll substitute their values. And we're done. Yeah, so this one's a little bit more challenging. We learned a couple of new things. So just to review, keep in mind this denominator was quadratic, so the numerator had to be linear. That was a new thing that we learned, okay? And then I also introduced you to this new technique, which is converting everything in general form, and we call that technique equating coefficients, because after we convert everything in general form, we equate the coefficients, and that usually turns out to be very simple work, and it allows us to solve for the variables, which ended up being numerators for our partial fraction decomposition. So do you feel smarter? Yes, I hope you do. All right, so let's move on. Time to try something new. So we're still doing partial fraction decomposition, but this time, this one's going to involve long division. Now, why is it called long division? Yes, if you remember, when we covered long division, it's because it's long. Okay, so let's just jump into it. Here we go. So the first thing to notice is the degrees of the two polynomials that we have. Okay, remember, degrees just means the highest power in the polynomial. So in the numerator, the highest one is the 4th power. And in the denominator, the highest power is the 3rd. So those differ by a degree of 1. The degree of the numerator is larger than the degree of the denominator. So that tells us that we can divide. It's the equivalent of an improper fraction. So remember, when you learned your arithmetic, when you had things like 3/2, you'd say, oh, the numerator is larger, so that allows us to divide 2 into 3. And we'd say goes once, you subtract, and you get a remainder of 1. So the answer is 1.5. Because you get the remainder, you put it as a numerator, the divisor as a denominator. Okay? So we're going to do exactly the same thing, but with this much more complicated rational expression. Remember, rational expression just means fancy fraction. Just think of it that way. Okay? All right, so let's jump into it. So we set up the long division, and we just jump into it. So we're going to need to multiply the x times the x cubed to get the x to the 4th. We multiply the x times the 2x squared, which gives us a 2x cubed, and the x times the x gives us the x squared. Now if you remember from long division, Now we change the sign on them. In other words, we subtract them, and we end up getting 5x squared. Okay, so the x to the fourth, those were 0. These were also 0. And then the 6 minus, remember we are subtracting, the x squared gave us a 5x squared. Awesome. Now we bring down the next two terms. We check the degree of the divisor, which is a cubic. And over here we have an x squared, so that means we're done. We can stop now. So the answer is the x that we had, and then this right here, which is the remainder, becomes the numerator. So plus 5x squared, 20x plus 6. We divide that by the divisor, and we're done with the division part. So yeah, this problem's going to be a little bit long. So let's move the answer up here so we can make some space. Feel free to rewind the video and go over the long division again if I went a little bit too fast for you. Okay, so now what we do is we focus on the fraction and we do it just like the problems that we've been practicing. So what do we do first? We factor the denominator. Okay, so the first part of the factoring is pretty easy because the x cubed, the x squared, and the x, all three of those contain the x, so that's what I factored out. I factored out an x over here. Now let's just focus on the fraction part because the x, well, we're not going to have to do anything with that. So let's just focus on that fraction. So we continue with the factoring. So the trinomial factors out into two linear factors that happen to be identical. X plus 1 times x plus 1. So of course, we can rewrite it as x times the x plus 1 quantity squared. All right, so now we're ready for the setup of the partial decomposition. Okay, so check out the setup. I want you to stare at it for a little bit, see if you can figure out what I'm doing. So of course, the first x, remember that one, that's exactly what we've been doing, okay? You just set it up as a constant over that variable x. Now the second fraction, where did I get this one? Well, notice that we have a repeated linear factor. Don't think of it as a quadratic, because the x is not squared. So it's a linear factor, it just happens to be squared. So what we need to do is first put it to the power of 1, and then of course the numerator is still just a constant. So we just put b over the x plus 1, and then we still need another fraction, but this time you're going to include the linear factor squared, okay, which is this one right here. But again, don't think of it as quadratic because it's a linear factor squared. Which of course, if we expanded it out, it would be quadratic. Don't think of it that way. Okay, so we've got our setup. Let's just clean it up a little bit. There we go. So remember, we multiply the whole equation by the lowest common denominator, the LCD, which of course is equal to the x times the linear factor x plus 1 quantity squared. Okay, so we're going to multiply it how many times? This time we're going to multiply it 4 times. And what's going to happen to all denominators? Starts with a P, ends with an exclamation mark. Yes, poof, they're all going to disappear, okay? They're going to be goners. So let's write out the answer. On the left-hand side, we're going to have the 5x squared plus 20x plus 6. In other words, we just canceled out the denominators. Now on the right-hand side, that's where it gets a little bit interesting. So we get an a times the x plus 1 quantity squared. The second term, do you want to give it a shot? What do you think it is? It's going to be b times an x and an x plus 1. And finally, the third term on the right-hand side is just going to be c times x. So nice. Now we don't have any more fractions. They're goners. Poof, they canceled out. So we're ready to solve for a, b, and c. Now remember, in our toolbox, what do we have so far? Well, we have two techniques. Do you remember what they are? First one was strategic substitution. And the second was equating coefficients. Now, sometimes you can use one or the other or a combination of both. It doesn't matter as long as you figure out what the a, b, and c are. Both techniques work out pretty well. I just happen to like the strategic substitution quite a bit because sometimes it's really, really quick. For example, for this one, I'm going to let x be equal to 0 and check out what's going to happen. We're going to have a 0 here, 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 and here. So very nice. Everything cancels out and we are just left with a is equal to 6. Now let's go back, and every place we see an A, let's go ahead and substitute a 6 there. So we're going to plug in a 6 right here and a 6 right here. Nice. Now let's go ahead and try and solve our B and our C. This time, let's go ahead and let the x be equal to -1. Now again, we call it strategic because I'm not just picking these numbers out of the blue, right? I'm looking at the factors. For example, this linear factor right here is x plus 1. So if I plug in a -1, that's going to make that whole term 0. And when you make things equal to 0, they disappear and they allow you to solve whatever's left over. Okay, so check it out. So we're going to plug in a -1 every place you see an x. Okay, so a little bit of arithmetic, but no problem. So on the left-hand side of the equation, we're going to be left with 5 minus 20 plus 6, which is -9. On the right-hand side, any term that contains the x plus 1, when we plug in the -1, it's going to be 0. So these two terms are going to end up just being 0. They're going to cancel out and disappear. And we're left with the last term, which is c times x, which would be -1. So that makes that one -c. So let's write our answer here. So c is equal to 9. So now we've got our c. Now let's go ahead and substitute or replace c's with 9's. All right, so we're almost done. Let's just clean up a little bit. So you see the strategic substitution works really quick and really well. Now we could, from here, go ahead and use the equating the coefficients, but it's going to be a lot of work. Check it out. I'm going to show you a trick here. So we're going to stick to the strategic substitution, but what do we plug in now? Because the 0 worked out pretty well and the -1 worked out pretty well. Now you can pretty much plug in whatever, because all we need to do is solve for b. Now, I did say whatever, but don't plug in a fraction or anything that's going to make the computation a little bit difficult. Pick an easy value. Okay, so I'll tell you what, we had pick 0, we had plugged in -1. Let's plug in +1 and you'll see what happens. Okay, so every place we see an x, we're going to plug in a 1. On the left hand side, we're going to have 31. And on the right hand side, we're going to have 6 times 4 plus b times 2 plus the 9. So a little bit of arithmetic here. So we're going to get 31, subtract the 24, subtract the 9, and divide that answer by 2, and we should get an answer of -1. And we are done, guys. That is it. So let's go hunt down all our b's. So we had a b right here and a b right here, and we're going to plug in -1 right there. Okay, so let's just write our final answer because we are done. So I'm going to clean up here. So cleaned it up. It looks much better. Now, this fraction, which is what we applied the partial fraction decomposition to, was just this part. Okay, it was just in factored form. So now what I'm going to do is I'm going to write the final answer. So that is that x plus our fraction, which we've broken down. We've decomposed it into 3 different fractions, which are these 3. So it's going to be 6 over x minus 1 over x plus 1 plus 9 over the x plus 1 quantity squared. And that, my friend, is the final answer. Darn, this was a tough one. Okay, so yeah, a couple of new things here. So we have to use the long division. And now how do we know to use the long division? Remember, you look at the degrees of the polynomials. Since the degree of the numerator was larger, this one was larger, that gives you the green light to use long division. So pat yourself in the back, congratulate yourself, because this was a tough problem. So if you see something like this on the test, no problem though, right? Alrighty, let's try something else. Let's move on. Yay, so we're getting good at these. So on this one, we'll go a little bit faster because I think we're doing well. So what was the first step? The first step was the F word. We factor the denominator. That's the first thing we always do, okay? If it's not factored. So we have a binomial, both terms have an x, so we factor out the x, 1x. So we're left with a linear and the quadratic factor. So we copy the numerator and then we set up our partial fraction decomposition setup. So for our first fraction, we're going to have the linear factor, which is just x in the denominator. And then of course, our numerator is just some constant a, which we don't know. That's what we're looking for. For our second fraction, the denominator has a quadratic factor. So this is where sometimes people get a little bit lost. So since we have a quadratic factor in the denominator, the numerator has to be 1 degree less, which means linear. So denominator is quadratic, numerator is linear. Always, that's always the rule, okay? Whatever the power is of the denominator, you subtract 1, and that's what goes in the numerator. Now, if you're wondering, what about the first fraction? How did that work? Well, that also holds what I told you about the powers. Look, the denominator has a power of 1. We just don't put it on there, right? Now on top, we just have an a. Now that's a constant. Constant just means a power of 0. In other words, that's why we don't have a variable here. See? There's no variable there. No x there. Just the constant a. So let's get ready to get rid of those denominators. Now how do we do those again? How do we get rid of them? We multiply everything by the LCD. Now by everything, I mean everything inside the blue brackets. So at LCD, we're going to multiply it in how many times? Once times each fraction. And there's 3 fractions, so obviously 3 times. So here we go. So on the first one, the whole denominator cancels out, so that we're only left with the numerator, which is 2x squared minus 5. The first fraction on the right-hand side, in that case, we only cancel the x's. So we're left with the a and the quadratic factor. And for the last fraction, we're left with the bx plus c times an x. Okay, nice. So see, all the denominators went poof. All right, so now we're ready to start solving for a, b, and c. So let's start with strategic substitution. I'm going to let x be equal to 0, and that works pretty well because when you plug in the 0, everything pretty much cancels out except on the left-hand side, we're left with a negative 5, and on the right-hand side of the equation, we're left with the a. So we've solved for a. So now what I'm going to do is I'm going to go replace AC and a with a negative 5. Nice. Now what I'm going to do is I'm going to switch over to equating coefficients. Now we could continue with the strategic substitution, but in this case there's nothing nice that we could plug in. So we could plug in just values like, for example, 1 and then plug in a 2, and then we would set up a system of linear equations. So you're welcome to try that. It also works. But I think it's going to be a little bit easier to switch over to equating coefficients. Now on the left-hand side of the equation, notice I put in an extra term, the plus 0x. What is that? Well, that's just a placeholder. Again, I can put the 0 in front of the x. It still means 0. But I want to put that in there so that on the right-hand side, when we end up with a term that has an x, we can equate that to 0. Now let's go ahead and simplify the right-hand side. So on the right-hand side, we ended up with 4 terms. We've got some like terms here that we can combine. So we end up with b minus 5 quantity x squared. So those are the 2 terms that have the x squared. I just factored out the x squared. And then I put the linear term, which was a cx, and then finally the constant. So check it out. This right here is the coefficient of the x squared on the right-hand side. Now on the left-hand side, what is the coefficient of the x squared? Well, that's 2. So that allows us to set up an equation here off on the side. So b minus 5 is equal to 2. So we solve for b, and b is equal to 7. Great. So we got our b now, and we're still missing the c, but what we're going to do now is check it out here on the right-hand side. The c is the coefficient of the x, and on the left-hand side, we said the coefficient of the x is 0. So then the conclusion is z must be equal to 0. So we're done, guys. We solved for a, b, and c. So now I'm going to get the values for the b and the c. I'm going to plug them back into our setup, and we are done. Okay, now I'm just going to clean everything up and summarize what we just did. So I'm going to rewrite the final answer. This is minus 5 over x plus 7x over the x squared plus 1. So that answer is fine, but we could also rewrite it and eliminate one of the signs by putting the second term first and the first term second. So nice, we're done. So this right here is a partial decomposition of our original rational expression. Remember, it's important to learn all the vocabulary because a lot of times we're talking about really simple things, but we just use big fancy words, right? So the rational expression, all that means it's a fancy fraction with a bunch of variables on it, okay? All right, so we are done with this one. So hopefully you're feeling a lot more comfortable with the partial fraction decomposition and learning some cool algebraic techniques. Okay, let's try some more. Whoa, what about this one? Yeah, so what do we do here? Because we're supposed to factor, but how do you factor that? Well, the good news is it's already factored. So the only thing we have to worry about is to set it up correctly. So let me show you how to do that. So for the first fraction, you put the quadratic factor, x squared plus 2, to the first power. So in this case, if it's the first power, since it's the first power, we do not need parentheses. And then, like we did on the previous problem, since the denominator is quadratic, the numerator has to be linear. So ax plus b. Okay, now what about the second fraction? Because we need another one, right? So for the second fraction, we put the same quadratic factor, except that this time we raise it to the second power. Now, if that original power, this one over here, was, let's say, a fourth power, then we would have to write this to the first power, second, third, and fourth. We'd work our way up all the way to the fourth power. But thank goodness, I don't think you'll see something that complicated, okay? So I'm just giving you a hypothetical situation here. So again, good news, we didn't have to factor denominator because it was already factored. Now we just worry about the numerator for the second fraction. So same as before, since the factor is a quadratic factor, it just happens to be squared, so we call it a repeated factor, but that's okay. We still go by what's inside the parentheses. It was quadratic, so we drop it down a degree, a power, and again, the numerator has to be linear. All right, so things should be going a little bit smoother now because it's about the sixth problem that we do now. And so we find the LCD, which was the x squared plus 2 quantity squared. We're going to multiply that in how many times? 3 times. Ones times each fraction inside the brackets. So remember, this is what I've been calling the poof step. After you multiply the LCD, all the denominators should poof, cancel out. Every single time, okay? This technique should always work. If not, remember, you made a mistake. Go back, figure out what you did wrong. So for our first fraction on the right-hand side, so let's go a little bit slow here so nobody gets lost. We're left with our numerator, which was, of course, the ax plus b. But that quantity has to be multiplied times 1 of the x squared plus 2. Because the LCD has 2 of them, we only had one in that fraction, so only one of them canceled out. So if you got lost there, think about it, pause the video, think about it, and then move on. For the second fraction on the right-hand side of the equation, we have the cx plus d, but this time the whole denominator canceled out. So we don't need parentheses because there's nothing to multiply it by. Okay, now if you had put them in, no problem. So for this problem, you could try the strategic substitution and set up some system of linear equations, but I think it's going to be much more complicated if you do that. The easiest technique for this one is going to be equating coefficients. That's the technique we're going to use. So on the left-hand side, I just rewrote the polynomial in general form, and I put placeholders for every term that was missing. Okay, so we didn't have an x squared term, and we didn't have a constant, so I just put in zeros there. Okay, because we're going to use those when we simplify the right-hand side. So on the right-hand side, we have to do a little bit of work here. So we're going to have to FOIL these two binomials, FOIL multiplication. After we FOIL, we still need to rewrite these last two terms. And then I'm just going to rewrite them in descending order in general form. So we put the cubic term first, the quadratic term next, and then we're going to have some like terms here because this term and this term contain x's, just x to the first power. So those are linear. So I'm going to combine those two. So that's 2a plus c. And then I factored out the x because both those terms had the x. So that's our linear term. And then finally, we look for our constants, which we have 2 of those. So that's the 2b plus the d. So I'll just throw those at the end. Now I don't need to, but I'm going to put both those in parentheses just to emphasize that those two make up the constant. In other words, none of those have a variable. Keep in mind the b and the d, those are not variables, those are constants that we don't know, but they're not variables. The only variable we have here is the x. Okay, I think we're ready. Let's solve it. So let's start with our cubic. So the coefficient on the right hand side is an a, and on the left hand side we have a coefficient of 8. So that was an easy one. So a is equal to 8. Boom. All right, it's downhill from here, guys. So let's go to our square terms. So on the left-hand side, we have a 0. On the right-hand side, we have a b. So b is equal to 0. Now we look at the linear term, which is here. So that's a 13, so I'll put that up here, 13. And on the right-hand side, well, we do have a 2a plus c. So I'm going to write that up here, 2a plus c. So that's a little bit of a problem, right? Because we have one equation and 2 unknowns. So how do we solve that? Well, we need another equation, or we need to know what one of the two variables is. But wait a minute, we already know what the a is. We had solved for a already. So this right here is an 8. So we plug in an 8 and then we solve for c. So 13 is equal to 2 times 8 plus c. So c is equal to -3. We're almost done now. Now the only thing that we're missing is d. D is in dog. Okay, so what are we going to do? We're going to look at the constant, which was 0 on the left-hand side. But on the right-hand side, we had that 0 is equal to 2b plus d. But very similarly, remember, we do know what the b is. The b is equal to 0, so we're going to plug in a 0 there. So 0 is 2 times 0 plus d. So d is equal to 0 as well. Nice. So we are done. Now it's just time to clean up here and write our final answer and celebrate. Yay. So we erased all the scratch work, and now all we're left with are our answers for the A, B, the C, and the D. So I'm going to plug them back into our setup. And keep in mind, since the B and the D are 0, those we didn't really need to plug in, right? I'm just kind of, as a formality, I'm just plugging them in. But now I'm going to just write the final answer. So officially, I think you're almost experts at partial fraction decomposition. So I've got one more really nasty problem, and if you can do that one, then that's when I'll assign you your PhD in partial fraction decomposition. Just a little side note, we do use this in Calculus 2, so you see this a little bit in that course. Very useful skill. So on this partial fraction decomposition, it's going to include a repeated linear and quadratic factor. See, because we've got the x squared, which is linear, just happens to be repeated. So linear times linear is x squared. And it has a quadratic factor as well, which is the x squared plus 1 quantity squared. Now, I know this can be a little bit confusing because you might be thinking, wait a minute, isn't that quadratic? Well, we think of it as linear. It just happens to be repeated. Think of it as a linear factor. It just happens to be repeated. So x times x. That's why we just call it x squared. Now, the second one, that one's definitely quadratic, and it also happens to be repeated, which is squared. So I know the first time I saw this, it kind of threw me off because I kept seeing this as quadratic because we've been told when you see x squared, it's considered quadratic. I mean, it's just terminology. It's not that we're saying that it's not quadratic. It's we can think of quadratics as linear, repeated linear factors. Repeated how many times? Twice. So hopefully I didn't confuse you there, but that's necessary to understand so we can do the setup correctly. Okay, so here we go. So the first fraction, I'm just going to put a, the constant, over the x. The second fraction is b over the linear squared. Remember, it's a linear that's repeated. Third fraction, remember the numerator has to be a linear, so that's cx plus d over the quadratic. And finally, ex plus f over the quantity x squared plus 1 quantity squared. Okay, so there's our setup. So put on your seatbelts, here we go. Remember, the first thing is, well, I've been telling you, make sure that the denominator is factored, but in this case, the denominator is already factored. So we just skip that step. So now we multiply the whole thing by the LCD. So that being the x squared times the quantity x squared plus 1 squared. Young lady, I know you look confused, but just chill. We'll work it out. Just give me some space here. All right, here we go. Starting on the left-hand side, everything in the denominator cancels, so we're just left with the numerator, x plus 5. First fraction, one of the x's is going to cancel, and we're going to be left with the x times the x squared plus 1 quantity squared. Okay, so stare at it a little bit in case you got a little bit lost. Next term, the x squares cancels, so we only multiply by the x squared plus 1 quantity squared. The next numerator, well, it has an x squared plus 1 on the bottom, so one of those cancels, but we still need to multiply times an x squared and 1 x squared plus 1. Darn, you weren't lying to us. This is a difficult problem. Well, it's going to be long, but when we finish, you'll feel really proud because you're able to do a very, very complicated problem. Okay, I promise. So hang in there. Don't give up on me. Now the last fraction, it has an x squared plus 1 quantity squared, so that one's going to go bye-bye, of course. And we only need to multiply by the x squared. So remember, that's what we call the poof step, or what I call a poof step. Don't go to class and tell your teacher, oh yeah, the poof step, because they're not going to know what you're talking about, and they might think you're a little bit nuts there. Okay, that's what I call it. Okay, the poof step. Why? Because all the fractions just go poof. All the denominators disappear. Guaranteed to happen all the time if you multiply by the LCD. Okay, now notice I'm writing a little bit small. Prompt's going to be a little bit long. So from here, guys, we just get to practice our algebra and our focus, our ability to focus, right? Because it's really easy to make a mistake. So put on your seatbelts. Here we go. So in this one, I'm going to start looking and analyzing it. And it's like, can we use strategic substitution? Well, we could try plugging in an x equal to 0. And almost everything's going to cancel. And it's going to allow us to solve for one of the variables. Look, let me show you. So we're going to let x equal to 0. And pretty much almost everything cancels out except on the left-hand side, we have a 5. And on the right-hand side, everything cancels out except the b. Okay, if you want to take a second or two just to kind of look that through. Basically, what happens is when you plug in a 0 there, see, everything cancels out. Except this term right here, 0 squared plus 1 is just 1, squared is 1, 1 times b is b. So we ended up solving for one of the numerators already. So I'll tell you what, I'll go up here, I'll erase the b, and I'll put our 5 there, because we already know what the b is. And I'll also substitute in the 5 there. Okay, so let's clean it up now. So now, again, we could continue with the strategic substitution if that's the only technique we knew, but there's no easy numbers to plug in anymore. Yeah, so from here, we could still continue with the strategic substitution if that's the only technique we knew, but we would just have to pick arbitrary values. If you're not familiar with that word, arbitrary, it just means that you choose them. So for example, you could say, well, I'm going to plug in 1. Why? Because it's easy to work with. And then you can plug in 2, and then maybe a 3. And each time you plug in a value for x, you would end up with a bunch of the unknowns and you would set up a system of linear equations. And then you can solve that using matrices or whatever your favorite technique is. But for this problem, it's going to be a lot easier to just use equating coefficients. Okay, so we're going to use that technique. So equating coefficients, here we go. So on the left-hand side, that's already in general form. I'm just going to leave it like that. So we just have a linear term and a constant term. And on the right-hand side, here we go. It's going to be a lot of work. So I hope you put on that seatbelt kind of tight. I'm going to go a little bit quick, okay? So the first thing I did was I just squared that binomial. Boom, there it is. That's that same binomial right there. So right here, I'm going to FOIL multiply those two binomials right there. And after I FOIL, I still have an x squared at the end, which is this one right here. And the last term, I'm just going to distribute the x squared into here. And the last term, I'm just going to distribute the x squared. Woo, that was a lot of work, right? Okay, I'm going to clean it up a little bit. I'm going to distribute this ax into the parentheses. I'm going to distribute this 5 into the parentheses. I'm going to distribute the x squared into the parentheses. And if you're following along, you should maybe email your algebra teacher and thank him or her for helping you out there because you're following along. But be nice to your math teachers. So be nice to your math teachers, okay? We're some of the coolest human beings on this planet. Well, not all of us, but anyway. All right. So very long problem. So if you're still with me, congratulations. Okay. All right. So darn, that's a lot of terms. But the good news is now we're going to start simplifying. Okay, combining like terms. So let's go hunt for the highest powers now. So we ended up with an a and a c that are both have x to the 5th, but there's no x to the 5th on the left-hand side of the equation. So that tells us that a plus c has to be equal to 0. Now that doesn't get us what a or c is. I agree. But we'll just leave it there. And as we look at some more of the terms, we're going to continue to set up some of these equations. So let's go look for powers of 4 now. So for those, we've got a 5 and a d. And on the left-hand side of the equation, we don't have x to the 4th. So that one also has to be equal to 0. But of course, we could easily solve for d here. So d is equal to -5. Okay, so I'm going to go every place I see a d. So there's a d here. And I'm going to put -5. And there's a d there. So I'm also going to plug in a -5 there. So that looks better. And we go up to the setup. So we just found the d, so I'm going to plug that up there as well. All right, so we got 2 of them now. So we erase the d. Now, notice that I still left the a plus c here because we still don't know what the a or the c are. So, but we'll keep working on, okay? And I'll tell you what, the terms we've already used, we could actually just erase them. Now, on your paper, you could, if you're working on a paper or something, you just scratch it off. So we took care of the powers of 5. We took care of the powers of 4. So what's next? Powers of 3. Okay, so let's go hunt those down. This one, and this one. So we have 2a plus c plus e, and those are also equal to 0 because again we don't have an x to the third on the left hand side of the equation. Okay, so I'm just going to leave that as is for now. Okay, so let's get rid of those terms. That way it looks a little bit cleaner. And I'll tell you what, since the order we do them in doesn't matter, so what I'm going to do is notice that on the left hand side we do have a power of 1, a degree of 1 on the x. So let's go ahead and look for the x's, see what we find on the right hand side. Well, there's an x, and that's the only term, right? So that tells us that the a has to be equal to 1. Now, where did I get the 1? Well, that's the coefficient of the x. Remember, if there's nothing in front of it, it's understood to be a 1. So 1 has to be equal to the a. So bingo, we got our a, okay? So I'm going to go up here to the setup. I'm going to plug in a 1 there. But also, look, remember this equation that we had here? We just solved what the a is. That's 1. So I'm going to write it up here. So that's 1 plus c is equal to 0. So then the c has to be equal to negative 1. So we just solved for another letter, the c. So I'm going to go up to the setup. Remember, we had our c up here. And we're going to plug in negative 1. See, so it's going a lot smoother now. And let's look at this green equation here. So we just set the a, well, we already know what a is, it's 1. We already know what the c is because we just found it, that's negative 1. And then plus an e, that's equal to 0. So that equation we'll be able to solve. And I'll solve that right here. So this is 2 minus 1 plus c is equal to 0. So e is equal to negative 1. So I'm going to go up to the setup where we had e. I'm going to put a negative 1 there. And we're almost done. We just need to solve for f. Okay, so let's go look for f. F is right here and it's in front of the x squared. So I'm going to look at all the terms that have an x squared. So that's a 10, a minus 5, and the plus f, they're in front of the x squares. And on the left-hand side, there's no x squares, so that's 0. So let's solve for f. So f is equal to minus 5. And we're done. So I'm going to go up to the setup. I'm going to substitute in the negative 5. So we solved for every single one of our constants in the numerators in the partial fraction decomposition. All right, nice. So I'm just going to clean everything up now, rewrite our answer. So it's 1 over x plus 5 over x squared minus x plus 5. What? Isn't it supposed to be minus? No, what I did was I got this negative and factored it out. Here it is. And it looks a little bit nicer, see? So I factored out the negative, just put it once in front of the fraction. So it's a little bit of math voodoo there for you. All right, and we'll do the same thing with the last fraction. So I'm going to factor out the negative, and we're going to be left with the x plus 5 over the x squared plus 1 quantity squared. All righty, so we are done. Did you count them? That was 3 dones. Congratulations. If you followed along, I should award you your PhD in partial fraction decomposition. So now you can do every single problem anybody throws at you, okay? I promise. Just practice these problems that we've been working through, and you have mastered this concept. So hopefully this helped you out. So say yeah.